So the partial of this one with respect to x would be, yeah, you said 2x yz, right? And this one with respect to y is also 2x yz. And this one with respect to z is also 2x yz, which is 6x yz. Okay, so the integral is going to be the triple integral across this region. So this is a box enclosed by a rectangular box enclosed with these boundaries right here. A, B, and C are also greater than 0. Okay, so it's 6xyz, and we can go dx, dy, dz. X goes from 0 to A, y goes from 0 to B, and z goes from 0 to C. Okay, so integrate in x, and we get 3x squared yz. That's from x equals 0 to x equals A. Okay, so put an A in there, you get 3 a squared yz. And then integrate with respect to y. And you're going to get 3a squared y squared z over 2. And then it goes from y equals 0 to y equals b. And that's 3a squared b squared z over 2 dz. And what is that? 3a squared b squared. And skip the last step, c squared over 4. Okay, so that's the answer to the first question. Any questions about that? Any concerns? Okay, let's do the next exercise. So number 2, use the divergence theorem to calculate this surface integral, the flux across S. Okay, so here, S is the surface of the solid bounded by the cylinder, and the planes x equals -3 and x equals 3. Okay, so let's try to get a picture of what this looks like. Here's our coordinate axes. Okay, so it's a cylinder y squared plus d squared equals 1. And then the planes x equals -3 and x equals 3. So let me come back here and call that -3 right there. And we'll come over here and call that 3. Okay, so it's going to be between here and here. There's, like, if you can imagine, a plane right here that's parallel to the YZ axis, and another plane over here that's also parallel to the YZ plane. And then you have y squared plus z squared equals 1. So this is a cylinder, and its radius is 1. Okay, so it's like, so if you just look, if you set x equal to 0 and just look at that, then it's going to be a circle that it's going to be a circle like that. Okay, and then when x is -3, then you have another circle. Oh, wait. And then when x is 3, you have another circle. Okay. Okay, so you have basically this cylinder here. that lies like that's laying on its side like that. And so the first thing is to figure out so this is going to be, according to the divergence theorem, that's the integral of the divergence of F dv over the inside of the cylinder. Okay, so we need to integrate over the inside of the cylinder. And the first thing is that x is between -3 and 3. So you can use that. That will be then the last part. But then we have y squared plus z squared less than or equal to 1. So that's going to be, you can set it up like this, r equals, so z is pointing straight up and y is over here. So you can set y equal to r cosine theta and z is equal to r sine theta. And then you have r ranging from 0 to 1, and then theta ranging from 0 to 2 pi. Okay, so that gives, so this right here gives you the whole circle and everything inside, everything in the disk. And then as x ranges from -3 to 3, then you go through the whole cylinder. Okay, so that's the information that we need to integrate across the whole cylinder. Now, let's calculate divergence of F. So what's that going to be?
Isn't it for, it's going to be 3y squared.
Yes. Okay, and then this one, this is with respect to y, right?
Right, so just be
0.
Yeah, that's going to be 0. And then this one?
Respect to x. It's 0.
With respect to z.
Awesome.
squared.
So x, y, z.
Squared.
Yeah, 3z squared. Okay, so that's going to be, actually, that's good, because that's going to be 3. Yeah, 3 times y squared plus z squared. Okay, so the integral is going to be 3y squared plus z squared dv. Okay, so that's what that is. But we switch to these polar coordinates. We'll have x go from -3 to 3. R goes from 0 to 1. Theta goes from 0 to 2 pi. Okay, this, all that becomes r squared. And then our integrating, and then our integral of this part is r dr d theta. Okay, so r dr d theta. But then you also have dx right here on the end. Okay, so now there's no, look, there's no x's in here. No x's. So that means that we just take this one minus that one, which is 6. Then there's no thetas either. So we take that one, which is 2 pi. 2 pi minus 0, 2 pi. And this is 3r cubed dr. Okay, so 12 pi. And this integral is what?
3/4 all to the power 4.
Yep, and from 0 to 1. So that's 3/4. This 4 is going to reduce that to a 3, and we have 9 pi.
And it seems a lot more simple than the stuff we did before.
Wait, what's that?
I feel like this is easier than the last like 2 sections.
I don't know about, well, yeah, you're just, yeah, because integrating across surfaces is not very fun. Okay. Now, okay, I will tell you, in this section, there were some problems that I decided not to use, which were stuff like find the flux across. So like if you take this object, if you take this cylinder right here, this cylinder has this side right here to it, but then it has this front side and the back side. It has this cap and that cap. And this flux, this right here represents the integral over this and the back side and everything. Okay, so there are some problems that said, okay, find the flux across, let's say, this part right here and this back side, okay, but not this front one or something, but not this side. So to find that one, you would have to take you'd have to do a surface integral of this over this and subtract it from you'd have to subtract it from this 9 pi. So you'd have to take a surface area here and subtract it from that 9 pi. So you'd have to do this integral, this surface integral on this part of it. And so that just gets to be kind of tedious because every part is really long to do and easy to make some mistake. And if you got 2 parts that you have to do and you can make a part and you don't get the right answer, then it's like, where did I make the mistake? Okay, and that's not very fun. Okay, so number 3, use the divergence theorem to calculate the surface area, calculate the flux across S. Okay, so let's first calculate, and then S is the sphere with the center of the origin and radius too. Okay, so we'll get to that in a second, but first of all, the divergence of F, let's calculate that one. What's that going to be?
Gonna be 3x squared plus 3c squared.
Yeah, so that's the partial of that one with respect to x, partial with respect to y, partial with respect to z. Okay, so that's nice. Okay, S is the sphere. So essentially what we're looking at, the integral that we're looking at is this integral over some 3-dimensional region of 3 times x squared plus y squared plus z squared dv. Okay, so I just copied and pasted all the spherical coordinate stuff because it's a sphere. I copied all that stuff there. Sphere with center of the origin and radius 2. So we need to find limits on rho and theta and phi. Okay, so what, and this is supposed to give us the sphere, or these limits right here, okay, they want us to find the integral over the sphere, which is just the boundary, but these limits here should be the ball, which would be the inside, which would be the sphere and the inside of the sphere. Okay, so first of all, rho, that's the, that's x squared plus y squared, that is the radius. So to get the ball, what do you have to put, limits you have to put on here?
Well,
0.
32 pi.
0 to 2, because its radius is 2. So that 2 right there. And then the next one is 0 to 2 pi, right?
Yeah.
Now the third one.
That just
Is it gonna be 0 to pi over 2?
0 to pi. Because you want the whole sphere. So so if this is z, and that's y. Going from here to here from here to here, that's going to be pi over 2. But you want to go all the way around, right? You want to go all the way to the bottom on all sides. Okay, so 0 to pi. Okay, great. So now we can set everything up. So 0 to pi on the phi, 0 to 2 pi on the theta, 0 to 2 on the rho. And this is really nice because that's just rho squared. And your dv, I've nicely wrote that there. So rho squared sine phi d rho d theta d phi. Okay, so this is what's this, 3 rho to the 4th. Okay, so what's the integral? Oh, and there's no, oh, there's a phi there, right? But there's no theta, right? So there's no theta?
2 pi.
Yeah, so you can put 2 pi out. But there's a phi there, so there's a sine phi, so yeah, you can't mess with that. Okay, so integrate this one, and you get,
3/5
yes,
to the power 5.
yeah. And that's rho going from 0 to 2. And then there's a sine phi, d phi. Okay, so if you put a 2 in here, so a lot of times, you know, you have you might be used to putting a 1 in, but now there's a 2. So, you got to put a 2 in there. 2 to the 5th is what, 32? Okay, so we're looking at 2 pi times 3 times 32 all over 5. And then we can integrate this one, so that's
Cosine.
negative cosine from 0 to pi. Now, if you put a pi in, cosine of pi is negative 1, actually. So that's actually going to be positive 1. And then subtract a negative 1, that's going to be 2. Okay, so all that's going to be 2. So we got 2 pi times 3 times 32. And this one is times 2. Okay, that's going to be 2. So we have all that, which I calculated to be 384 pi over 5.
Wow, you're still fast.
Well, I've learned my lesson. I do these problems ahead of time, make sure that they work out.
Not working.
So I tell you, it's very frustrating, and it's probably just as frustrating as you guys doing your homework.
Yeah, I have to extend my homework like a lot of times.
Yeah, like you get the wrong answer, and I'm like, what? When I get the wrong answer, then I have more resources to look at than you guys do. So, oh well. Okay, so any questions about this one? So this is using spherical coordinates on the volume integral. Okay, and then finally number 4. Okay, so it's a surface integral, and you're looking for the flux. And so here we have a paraboloid and the plane. So this is a solid bounded by the paraboloid and the plane. So let's take a look at what this looks like. Okay, so z equals x squared plus y squared. That means it's going to be here right at the origin. And the plane z equals 4, so we'll come up here to 4. So that's going to be the top of it. And so if you come out here to the value 2, that's going to put you up at 4, because when x is 0, y is 2, then z is going to be 4, which will be right on the plane there. Okay, so that means that the paraboloid is going to come up like that. And if you come over here, it's a 2. Then again, that's also going to be part of the, also hit right there. So it's going to be like that. Okay, and then if you look at the intersection of this paraboloid with this plane, okay, so the intersection is x squared plus y squared equals 4. Okay, so by setting z equal to 4, and that's a circle of radius 2, and that's going to be this circle here. something like that. Well, what the? That didn't look very good at all. Let me see. Let me try again. That doesn't look very good either. Okay, but anyways, it is what it is. Okay, so this is the paraboloid right here, the paraboloid there, and then this top right here. So kind of like the tip of a bullet if you stand it up on end like that. Okay. So I want to know the flux across this surface. So the surface includes this paraboloid, but it also includes this part of the plane, this top here. So the surface is that and this. That's what they're asking you to calculate. So if you're doing you'd have to do two surface integrals to find this. And set up two surface integrals to find it. Okay. So, but we can use the divergence theorem. So let's calculate divergence. And what's the divergence here? Partial of this with respect to x is just y squared, right? And then this one?
0.
Yay, 0. And then this one?
X squared.
Okay, so they do this like weird stuff like this cosine z and the sine z, and then like x e to the negative z, and people might be like, oh my goodness, the world is coming to an end. How can you possibly do that? Okay, but then it just all goes away when you take the derivative. So it's like, what? Okay. So anyways, it does not have anything to do with anything. It didn't contribute anything. This one and this one and this one, nothing to do with anything. Okay, so we'll go ahead and calculate the integral across the volume. So z, it's easiest. Z has the easiest boundaries, first of all.
0 to, oh wait, 4, yeah.
Not 0 to 4. So it's this, so you can tell from here, from there to there. So the bottom, so you can take like a vertical line segment that spans through the whole interior. The bottom boundary is going to be x squared plus y squared.
Hmm.
Okay, and then the next one, okay, the x's, the limits on x and y. It's easier if you shift to polar coordinates for x and y. And what's the limits on r and theta?
Wouldn't theta be 0 to 2 pi?
Exactly.
R is gonna be 0 to 4, 0 to 2.
0 to 2, exactly. Okay, so r goes from 0 to 2. And then I guess this right here is going to be r squared, right?
Yeah.
Okay, so that means we can set the integral up. 0 to 2 pi, 0 to 2. Wait, yeah, and then z goes from
X squared, no, R squared to 4. And Y squared plus X squared, or R squared.
yeah, r squared. This is r squared, right? So it's r squared.
And
And
another
then r.
dr. You said dr.
Yeah, so the area thing is r dr d theta. So this r right here is right here. That one there. Okay, so you have to get everything Good. Okay, so there's no thetas in. That's going to be 2 pi. Yay. If you integrate this, okay, this is r cubed, right? Okay, so you integrate that, it's going to be z, and you go from z equals r squared to z equals 4. Okay. Okay, you put a 4 in here, you're going to get 4.
all cube.
Yes. Minus, and you put r squared in, you're going to get minus r.
All to the power 5.
Exactly. Okay, so integrate that, and you have
4. Oh, yeah. Minus
this one.
r to the power 6 divided by 6. Mm-hmm.
Okay, so 2 to the 4th, that's 16. And 2 to the 6th is uh,
That's
64, right?
Yeah.
Okay, if you simplify that, that's 32 pi over 3.